Hi everyone. Today we're starting ethers and epoxides, and this is after the alcohol chapter. So basically, alcohols are an R group with an OH group, and now we're covering an R group with an OR group. And a lot of times H is replaced by R, and so we have some kind of alkyl group involved. So for ethers, they have a different kind of nomenclature and reactivity, but a lot of times it's somewhat similar to alcohols because of the O. But it's important to realize that they don't get deprotonated like alcohols, so they have a different kind of chemistry. So let's look at nomenclature first. With ethers, it's a little complicated because you have two R groups and they can be the same or they can be different. So if you have R groups that are the same, then this is called a symmetrical ether. And if you have two R groups that are different, then it's called asymmetrical. All right, so you guys are used to hearing about diethyl ether. So diethyl ether is symmetrical. Two ether groups, looks like a bat with wings, but diethyl ether, or just ethyl ether, because it's assumed then that ethyl is in both positions. But those two groups can be different. So you could have ethyl methyl ether, or you could have tert-butyl methyl ether. And sometimes this is rearranged to methyl tert-butyl ether, which is called MTBE, and that's a very famous ether in terms of it being in the news as a gasoline additive. People talk about MTBE. So this method of naming ethers is quite easy. You just go alphabetically, you name the two R groups separately, and then this part is taken care of by the word ether stuck at the end. It's funny, MTBE, by the way, it puts methyl tertiary butyl, but butyl comes before methyl. But everyone calls it MTBE, so just FYI, that one doesn't follow the rule, but normally we go alphabetically. Now there's another way of naming that's also very useful. Let's say you have a very long R group on one side and sort of a shorter one on the other. So it's very convenient to just call this as a pentyl group or pentane, and then you can just include that oxygen as an oxy group. So this is 2-carbon oxy group, which is ethoxy, and it's off this carbon 1, so it's called 1-ethoxy pentane. So that's an alternative name. Both are acceptable, and you should be familiar with both. Just because you may not have the option of being told one way or the other, you might be told randomly, this way, and then the next instance you're told this way. You need to just know and go with the flow. So my rule of thumb is, as a student, you should be prepared to listen to both ways and interpret it correctly. But if you're given a choice to name it, you should be able to name it at least one of the two ways accurately. So let's try using those rules. Go ahead and give these ethers a try. Keep in mind with the stereochemistry that you may need R and S for that one. And then for this one, it's a bit complicated, so you may use one method over another. We'll go through these in a couple of minutes. All right, we're back, and for the first one, you have an ethyl group on one side, an isopropyl group on the other. So just alphabetically, ethyl isopropyl ether. Okay, so that's pretty simple and straightforward. If you like the other method, you could also call it, this is the bigger group, so you could name it 1, 2, 3, longest chain is 3, so this is a propane. And then you could name this as a whole group called an ethoxy group, and it's off carbon 2, so 2-ethoxy propane is just as likely a name. For the second one, I like to call this ethoxy just because it's easier with a little bit more complication with the stereocenter here. So this is an S stereogenic center. So this is 1, 2, 3 priority. So it's going counterclockwise with number 4 in the back. This is S, and so this is S2-chloropropyl ethyl ether because C comes before E. But if you want another way to name it, it could also be S2-chloro 1-ethoxy propane. So that's also acceptable, and that's calling this a group or substituent off this parent chain. For the last one, I'm using a numbering system that has the smallest combination of numbers, 1, 2, 4. And so I have 2,4-dichloro, 1-ethoxybenzene, again using this as a substituent on its own, Or if you want to use the other method, you just name the two groups on either side of the ether, and then you stick the word ether on it. So 2,4-dichlorophenyl, because that's a phenyl group, and then ethyl ether. So, and that goes by chloro alphabetically versus ethyl, and then ether. And now let's try drawing these structures as well, which I always find easier to do than going the other way around. All right, guys, for this one, I see an R stereo isomer, so I have to make sure my 2-ethoxy, so this is my 1,1-dimethyl 2-ethoxy dimethylcyclobutane. All right, so 1,1-dimethyl, okay, so this is alphabetized by M. Di, tri, tetra, those aren't alphabetized. Iso is alphabetized though, and so is cyclo. So ethoxy comes before methyl, so here's that ethoxy. And then I had to figure out to put in the back because 1, 2, 3, so that looks like S, but if I put it in the back, that reverses it to R. I hope that makes sense. And this is a cyclobutane, so that's the parent. I often like to start backwards with nomenclature. I draw the cyclobutane first, then I draw the dimethyl, then I draw the 2-ethoxy, and then I figure out the R group. For part B, cyclopropyl, that's a cyclopropyl group. That's an isopropyl group, and then ether means there's an oxygen between the two R groups. Much easier, I think, to draw what they tell you. All right, in terms of structure and properties, what do we know about how ethers behave? So first, let's talk about why ethanol has the highest boiling point of these three compounds, whereas dimethyl ether is still pretty low boiling point. This means it's likely to be a gas at room temperature. And then this one as well, propane, is definitely a gas at room temperature, but ethanol is a liquid at room temperature. So the hint is it has to do with intermolecular forces. So what do you know about the strength of intermolecular forces based on functional groups like hydroxyl groups, ethers, and alkanes? You should know a little bit about that. And then also think about the change in functional groups and the change in boiling point in intermolecular forces as you go from dimethyl ether to diethyl ether to dipropyl ether. What's going on here? They're all ethers, so the functional group is somewhat constant. What's different are the R groups. So why is there a change in R group that's affecting the change in the boiling point property? Okay, so both answers should involve a description about the intermolecular forces. Go ahead and put down your best guess and we'll come back and discuss. All right, guys, this is the kind of question we've gone over in Chem 261 many times, which is intermolecular forces. The stronger the forces are between molecules, the more they stick to each other, the more energy it takes to break them apart. So those interactions get broken, which results in phase changes. So liquids, they feel attracted to each other. When you supply energy, they can get farther and farther apart. And now when they're far apart, they're in the gaseous state. So we're talking about boiling point, which is liquid to gaseous state. So for ethanol, the change in each of these, the way that I sort of think about it is you have to have a constant mass in order to compare the functional group. We see the functional groups are changing, but if the mass is also changing, then we can't say which factor is at play. So I generally count this as a carbon. A carbon and oxygen is 3 heteroatoms, so carbon and oxygen and carbon. So they're about the same molar mass, 12 for carbon, 16 for oxygen, so give and take a few AMU. But then here, dimethyl ether, carbon, oxygen, carbon. Again, 3 atoms about the same mass. Propane, C, C, C. Okay, 3 atoms. And then hydrogens, because these are all saturated, they're going to have same kind of molar mass here. So given the same molar mass, or approximately the same molar mass, what's changing is the functional group. We have alcohol or hydroxyl group, an ether group, and an alkyl group. So that's what's affecting the boiling point. So first is just recognizing what is the control variable, which is molar mass, approximately controlled. And then the changing factor is the functional group. Now we know with OHs that they form hydrogen bonds with other molecules with OHs or NHs or HFs. Highly electronegative atoms have a strong dipole. So those very strong dipoles are capable of hydrogen bonding. That's our strongest intermolecular force. So boiling point is going to be pretty high for molecules that can hydrogen bond strongly together. When you decrease that by doing dipole-dipole only, you don't have the hydrogen for a stronger dipole, you have sort of an intermediate dipole. So for dipole-dipole, it's got attractions, but it's not as strong as hydrogen bonding. It's pretty dramatic actually, right? 78 degrees to -25. So that's pretty dramatic a change. Propane has even weaker dispersion forces. You can see from its boiling point that it's quite decreased. So even though dispersion forces have a tendency to add up and they can become quite strong, think of oil molecules. Oils are usually in liquid state because those molecules really stick together. But these small chain alkanes, they don't really have very strong London dispersion forces compared to their counterparts, ethers and alcohols. So these are very weak in comparison in terms of their relationship to each other. Propane and propane, they don't really like to stick together too much. So these are the weakest intermolecular forces, so it takes the least amount of energy to break those apart into their gaseous form. When I say break apart, it doesn't mean they're covalently bonded. I just mean breaking the attractions between them that would create them to be liquids. Okay, that would cause them to be liquids. Those forces are broken. Now with the bottom half, we see dimethyl ether, diethyl ether, dipropyl ether. So same functional group, that's the control. What the changing variable is the molecular weight, so the molar mass. So as I add carbons, I add mass, I add electrons, and adding electrons adds the dispersion force factor. So intermolecular forces, or the London dispersion forces, increases with the more electrons you have, which is a function of mass. So increasing that will increase the strength of those London dispersion forces, and then those all add up and you can get quite significant. Look at dipropyl ether, 91 degrees Celsius for its boiling point. That's almost like water. Water's 100. So that's quite significant. So you never want to say London dispersion forces are weak. These are always relative terms. Common ethers used as solvents are diethyl ether. I know you've used that in laboratory many a time as a solvent, or in reactions like bromination, or these kinds of reactions we've talked about are often done in polar aprotic solvents like diethyl ether or methylene chloride, chloroform, carbon tetrachloride, things like that. Tetrahydrofuran is THF. We've seen that solvent in, BH3 THF hydroboration, or even oxymercuration. We've seen this reagent used as a kind of polar solvent that enables it's intermediately polar. It's very good at dissolving things that are polar and nonpolar all at the same time. So it's very critical to have a solvent like that. Also, these lone pair electrons help to stabilize charge intermediates, such as when we have partial charges on things, like on alcohols, for example. It helps to stabilize. Or even alkenes, which are what these are for. Alkenes, when you're attacking molecules, you need to stabilize these charges. And carbocations or carbocation-like intermediates need to be stabilized by some source of electron density that surrounds them. It really helps a lot with lowering the activation energy for reactions. So the solvent plays a very critical role. Sometimes you see molecules like this as well used as solvents because these ethers are usually somewhat polar. They've got a dipole, but they are also aprotic. They don't have the hydrogen that they don't have the hydrogens that alcohols have. So it's very useful to not have that and still be polar in some way. So number one is that these solvents are polar aprotic, which is very useful for stabilizing and dissolving all of your reactants. Number two, they have in general lower boiling points than alcohols and water, which allows us the practicality of boiling off the solvent when we need to. So if you're trying to isolate your product, you don't want a bunch of solvent diluting it. Maybe you just want the product in its pure form, or what we call neat, N-E-A-T. So if you need it neat, that means no solvent. So it helps to be able to boil off the solvent. If it has a lower boiling point, it's the first to boil off, and then you can keep your sample as a liquid.